Okay, so let us get back to where we left last time. So, we derived this relation for flux, diffusion of flux, and this has a form like this, minus and this 1 by 6 tau b alpha square, and then it is multiplied by concentration gradient. And since the flux is going in the direction where the concentration is decreasing, so there is a negative sign, and together we have lumped it together to call it dB. The term is dB. Now, there are few more things that we need to learn at this stage. One is, what is this tau b that we have already described as jump frequency, but this jump frequency can be further expanded to write like this: Z into nu into exp minus delta g m by RT. Where does this come from? So, let us say there is a site. So, let us draw. So, this is some material, and over here, so we were talking about interstitials. So, there are some interstitials, and let me draw it with different color. So, there is one interstitial over here, let us say one interstitial over here. So, now let us say this interstitial moves from here to over here. So, as you can see that this has lowest, and this is a low energy position, this is a low energy position. Somewhere over here it will have to have higher energy, and this will be your activation energy for migration. So, this is what I have tried to schematically draw here, is the energy plot when it moves from this position to this position. So, this is a one minima, this is another minima, and it has to go through energy, activation energy, meaning it must be provided this much energy before it can migrate, and this is the term delta g m, and we can therefore write it as some pre-exponential factor times exp this delta g m. Now, what this term will denote is the number of the fraction of jumps that will actually take place, meaning if delta g m is, if the energy for migration is delta g m, then the total number of vibrations that will actually result in migration is this fraction. Now, fraction of what? So, this is where this first term comes into picture. This is Z, this is the coordination number or site, neighboring sites where this atom can move. So, this is telling you the number of sites where it can move. What is nu? Nu is the in effect vibration frequency, or that is total number of attempts, you can say. So, nu is in any particular direction. So, for one particular site it is nu. So, it's for Z neighboring sites it is Z nu. So, this is the Z nu is the total number of attempts out of this fraction is that results in successful jump. So, that is where we get this relation tau b, and now if we expand delta g m equal to delta h m minus t delta s m, we get we can actually basically we can put together the thermal component and athermal component separately, and therefore, we will have something like this. This is Z. So, this is the thermal component, this whole is the athermal, meaning it does not get influenced by temperature. And now, when we put this back over here, what we get is that dB is equal to 1 by 6 alpha square Z nu exp delta Sm by R. So, this is like I said the A thermal component, and to it you multiply the thermal component, meaning the one which will get affected or which denotes how this value will change with temperature. So, this is your so, no matter what is the temperature, this value is supposed to stay like this. So, let me rewrite this over here in a new page. So, this comes out 1 by 6 alpha square z nu exp delta Sm by R exp minus delta Hm by RT, which can now be written like something like this: d naught exp minus delta q 1d by RT, where delta q is equal to delta Hm. So, in this particular case, which is the interstitial diffusion, which is written as ID. So, delta q ID is equal to delta Hm, meaning the activation enthalpy for migration, this is equal to delta Hm, and you would see why we are writing it like this, because in the next part it will get changed. So, this is your form of the relation dB, which is used to define the flux, you remember. So, now these are some two important relations with respect to interstitial diffusion. So, these are our relations which define interstitial diffusion. Now, next thing that we have seen how this interstitial defect has led to diffusion, and we have derived a relation for this, and this is how it comes down to. So, this is the flux is proportional to the negative of concentration gradient, and there is a proportionality constant. This proportionality constant has a thermal component and thermal component. So, this is how it looks like, and the activation energy or that enthalpy is so activation energy is related to this dB, and when we separate the entropy term and the enthalpy term, this is how this relation would look like. Now, let us look at two different conditions for this. One is steady state and one is non-steady state diffusion. So, when we say steady state, what does it mean? It means that del C by at any particular x by del T is equal to 0, meaning the concentration at that particular x is not changing with time. And you will see that this will only be possible when you have a concentration gradient like this. It has to be a straight line like this. However, if you have a concentration gradient something like this, will show that this is a del C by del T here is not equal to 0, which is what is called as non-steady state. So, now let us move ahead to describe this non-steady state diffusion. So, let us say this is a bar, and for this the concentration gradient is given like this, Cx, concentration is moving like this. This is we are talking about x, this is at some distance x plus delta x. So, similarly, we draw here this is some distance x and this width is delta x. So, we will call this plane 1, we will call this plane 2. So, let us say the flux of atoms across plane 1 is given as this J1. So, the flux of atom across plane 2, and we can call it something as J2, and let us say the area, because we will need this, which will get cancelled out eventually, but let us say that for now this area is A. So, now this J we know will depend on two things, one is D and the other is, right now I am not writing in differential form, because let us say we are talking about a little longer width. So, we are putting it like this, delta Cb by delta x. Now, what we need to calculate? We have already said that this is a condition where del C by del T is not equal to 0. Therefore, we need to find or calculate C as a function of x and t. Now, let us say that number of interstitial B atom that diffuses into the slice in this small slice is J1 A delta T. So, J1 is per unit area per unit time, and if we are giving it time t and we are talking about this area A, then therefore, the number of interstitial atom that gets into this is that diffuse into the slice in time t. So, we have already described some time. Okay. So, flux is number of atoms per unit area per unit time. So, we are talking about now number of atoms. So, we have to find what is the area and we have to find what is the time. So, we have both the quantities here. So, this is J1 A delta T. Okay. So, and similarly, concentration of atoms that would increase is equal to, now if something is going in, so similarly we can find what is going out, and that will be equal to so I have missed this part. This is going out will be equal to J2 A delta T. So, the concentration of atoms that would increase. So, obviously the number that is coming in is higher, because the that concentration gradient is higher at x and lower at delta x, x plus delta x. So, going in is equal to J1 A delta T, going out is equal to J2 A delta T, where J2 is smaller. So, now J1, so the number of atoms that has increased over time is equal to J1 minus J2 A delta T. But we know that J2 is equal to, and and we are talking about concentration. So, we have to divide by delta x. So, J2 is equal to J1 plus del J by del x into del x. This is again approximate. Now, putting this over there is del Cb by del T, putting the del T over here from this side to this side, and J1 minus J2, this is to be divided by delta x. So, we can get J1 minus J2 by delta x from here, which will be equal to minus del J by del x, because we have divided by del x. So, this is over here, which is now if we take it in the limiting case, then this will become minus del J B by del x, or in other words del Cb by del T is equal to del by del x we instead of JB we will put the relation we already know from first law, which is equal to dB del CB by del x. Now, this is what is called as continuity relation, which is also commonly known as Fick's second law. Now, here we can make an approximation that this quantity dB is if dB is approximately constant through the range, then we can further simplify it to write it like this. So, both these relations would be called the continuity relation. Basically what it is saying is that the concentration, the overall concentration of the total number of atoms remain constant. So, there is a particular flow of atom and we are just maintaining the continuity of this. So, you can see that where we started from, we just started from that there is a concentration which is changing with x, and therefore, there are two different fluxes at two different x's. From there we get a relation like this, and what we are able to see is that therefore, del CB by we are in a position to find a relation for concentration in terms of x and t. So, this is in the differential form, and when you solve it depending on the initial condition and the final conditions, then you will be able to get, this will give you CB as a function of x and t. So, this will have to be solved depending on initial and final conditions. So, the only thing that we have talked about here is the change in concentration. Now, if you put this as a straight line, what will happen? Del 2 CB by del x, what will this become? This quantity will become 0, del CB by del x will become constant, and del 2 CB by del x square will become 0, and therefore, you will see that del CB by del t comes out to be 0. So, as I said that the steady state will only be possible when you have a straight line like behavior for concentration. So, this is the steady state when del CB by del x is equal to constant, and whenever there is a curvature, then you would know that it is non-steady state. Now, let us talk about some applications. So, now we have seen the relation for Fick's first law and Fick's second law, which were derived assuming interstitial diffusion. We will also talk about the other kind of diffusion, which is when you have substitutional atoms, but before that let us look at some applications. Now, let us say you have cast an alloy. Let us talk about a simple alloy like a copper zinc, which is supposed to be and we are talking about 5% zinc. Up to 30% zinc you are supposed to get single phase, but let us say that because of the casting condition or because of difference in the weight, atomic weight of the two, there is certain compositional difference from point to point, and just as a matter of understanding, to understand this concept in a better way, we will assume that this concentration, let us say we are talking about zinc concentration, then the zinc concentration should have been 5%, which is given by C bar, but because of different conditions, different solidification condition, or like I said, because of the mass conditions, there may be some segregation, and therefore, you end up with a constitution, a compositional variation like this. So, this is not desirable. We would have want that when you say copper 5% zinc, it is uniformly homogeneously distributed, and therefore, comes the concept of homogenization. How does this homogenization takes place? It takes place by diffusion. So, right now copper and zinc, they are not actually interstitial diffusion. So, what I will do is I will replace this example with let us say iron carbon, where let us say we are talking about as small as 0.07% carbon. Okay. So, as you would see later that the equations are similar in form, only that the delta G value would change, but since we have only talked about interstitial diffusion. So, I will stay with this particular example, which is where carbon stays as an interstitial, and let us say with this is the 0.07%. So, this should have been your this is carbon, and this will become your C bar, and this is the maximum and minimum that is varying, and this is a completely theoretical framework. You are assuming a very you can say systematic fluctuation in the concentration, but this will let you understand what a homogenization means. So, let us say this is the concentration, C is equal to C bar plus beta naught, where beta naught will become, beta naught is nothing but the amplitude. So, this is the wave 2L will be the wavelength. So, L is the half wavelength. So, this is given here over here. You could have as well written it as 2 pi by lambda, where lambda would be the wavelength times x, but since we have taken wavelength as 2L. So, 2 cancels out and you are left with pi by L times x. Now, here since it is also varying with time, you would be able to see that the solution for this, once you put in that relation, it will come out like this. So, now what it is saying is that if we were looking at this, this is just telling you the concentration variation with x. When you look into this, this is also telling you how the concentration, this part as if you ignore this part, then it is only telling the concentration with x, and when you include this, it is also telling concentration variation with time. So, there you have T, which is varying, which is starts from 0 and changes, but tau is a constant. What is tau? It is given by L square by pi square dB, and it is equal to a constant. So, you can see all the quantities here is a constant. So, it is in this respect that you are calculating time. Now, what will happen when you increase time? How should this plot change? This according to this solution that you have obtained, if you solve using the relation we derived earlier, you would get something like this. So, this is, let us say this is T equal to 0, this is T equal to T1, and you can realize that or imagine that when you go to even higher time, it will become something like this. So, what is changing here? It is the amplitude. So, basically you can also write a relation for how the amplitude is changing, and you can say beta is equal to beta naught, which is the amplitude at the very beginning, exp minus T by tau. And this is nothing but concentration at x equal to L by 2. So, basically if you start from L equal to 0 here, x equal to 0 here, then x equal to L by 2 is what you are getting from this relation. So, this is the same thing, but we are only putting x equal to L by 2, and you will get how the amplitude is changing with time. So, in this particular problem, the way we have framed it, what is changing is primarily, not primarily only the amplitude, but that itself is now making the concentration homogeneous. So, here you can imagine the variation was from plus beta naught to minus beta naught, and that has changed from a much smaller quantity. Let us say it is 1/4 of beta naught. So, 1/4 of beta naught to minus 1/4 of beta naught. So, that is how this homogenization is taking place. So, in the end what you will get, completely homogenized in terms of composition. and if I want to plot it over here, then let us this should be the ideal final solution. So, the concentration has reached the expected value across the volume. So, here we have looked at only one x or in only one direction 1D. So, these problems are being solved in 1D, but the same can be extended to 3 dimensions. Next example that we will look at is carburization. Why would you want to carburize something? Now, again this is example related to steel. So, in steel you add you may want to add carbon only on surface. Why? Because when you add carbon, what happens? This is, so if we plot percentage carbon and if we plot strength, then you would see that strength actually increases up to certain value. On the other hand, if you look at ductility, so at this point you would be imagining, okay, very good, carbon percentage, we can keep the carbon percentage throughout the material very high and we will get very high strength. But then when you look at the ductility plot, then you would realize that it is not always a good thing, your ductility would drop sharply with increasing carbon percentage. So, what is happening is that maybe the total toughness is same, but this material, when you have very high percentage of carbon, if it develops cracks, it will fail very easily, and therefore, it will not be suitable for any component, and therefore, you do not want the material ductility to drop. But at the same time you are getting much higher strength, and along with that you are also getting very good wear resistance. So, wear resistance also increases. So, this is ductility, this is strength, and the light blue one here is wear. So, another important characteristics when you increase carbon percentage, which is actually direct effect of increased strength, is that wear resistance increases. Now, let us say you are talking about gears. On the surface, the gears are in continuous contact with the other gears, they mesh, so they move and slide onto each other. What does that do? That means that it is slowly eroding each other, and therefore, you need high strength and high wear resistance on the surface. And from this plot you can see that if the carbon percentage was very high, then wear resistance would be high, strength would be high, but at the same time you do not want the gears to fail from interior. So, what you can do is that have carbon concentration high only at the surface and not in the interior, and therefore, this process of carburization comes into picture. So, now if you are talking about, let us say, so this is a gear, what you want is that carbon is high only up to certain region, only near the edges. Why would you want to increase carbon concentration throughout the surface, throughout the bulk? That will make it brittle. So, you would increase carbon concentration only on the surface, and this is done by exposing it to very large carburizing atmosphere. And hence you would be able to get very high concentration only on the surface. So, we will look at how this particular carburization process, not how, but the diffusion mechanics of this particular process carburization in the next lecture. And in the meantime, it will be good if you can try to go through and this process carburization and understand what does it actually do and how is it useful. So, we will see you in the next class.